Hello everybody, I'm Mauro Vallati and this is a joint work with Lukas Chrpa. And let me just give you a very brief summary of the assumptions on which we are basing this work and on which is based domain-independent planning. So in domain-independent planning, we have a clear division between the planning engine, so where the logic of the planning process, of the search process is, and the knowledge model. The knowledge model, well, the knowledge about the domain and about the problem that you want to solve is encapsulated. And planning engines right now are more and more used in real-world applications. Problem is that they are designed and tested on good quality models. So if you think about the traditional benchmarks which are used for assessing planning engines, they come from the international planning competition and they are awfully of good quality. And what are the aims of this work? Well, we want to investigate the robustness of domain-independent planning engines with regards to issues in the input knowledge models. So we basically want to test how robust they are when something is not exactly of good quality. And a major point of this work is to raise awareness of the impact of maliciously modified knowledge. So as planning engines and planning systems are more and more used in the real world and in real world applications, some of which are also safety related, they are becoming more and more likely to be targets of attacks for cyber attackers. And specifically, in this sort of work, we are taking an attacker's perspective. So we are playing the role, we are acting as an hypothetical attacker that want to reduce or want to modify the way in which the planning system is working, possibly for a competitor or possibly for someone that he doesn't like particularly. And the easiest way, actually, to attack a complex planning framework is probably by targeting the inputs, so by targeting the knowledge, domain models, and problem models. And that's exactly what we are playing at here and what we want to investigate. And the standpoint that we are taking so is that we want to attack planning system and we want our attacks not to be detected. So we want to modify the knowledge models in a way that the post-hoc analysis won't show anything which has been manipulated or modified. So we don't want our modification to be clear and apparent in the solution plans. Issues in the models, of course, we are modifying the models which are provided in input. These issues can only be spotted by an expensive and time-consuming inspection. We are attacking it, but basically this is also mimicking the typical case of accidental complexity, when you are initially encoding new knowledge, for instance, and you forget something or you just put too many preconditions or too many effects, and suddenly something is not working as expected or is going very slow. That's exactly the other kind of perspective that you can have of this work. Malicious attack and accidental complexity. And in order to support this sort of standpoint, we introduce the formal notions, you can find that in a paper, about plan equivalence, which means two models are able to produce exactly the same set of planning solutions, and plan dominance, when one model is able to generate a set of solutions which is strictly larger than another model. And these are, of course, defined into the papers, and you can find them in there. And we identified three cases, and formally defined, of course, in the paper, that can satisfy that notions, particularly of plan equivalence, so that you don't want anything to be apparent from solutions. And these three cases are increasing the number of objects in the problem, and then two of them which are targeting operators in the domain models. But let's start with the increasing of number of objects. This is probably the easiest way to modify models, particularly if you expect problem models to be automatically generated, maybe because the planning framework is included in a larger autonomous framework, which is automatically creating models and solving problems while it's working. And the question then is, if we want to do some sort of malicious attack, is how to make sure that those objects will not appear in solutions. Well, of course, objects must not appear in the initial state, otherwise they can be considered by operators. They must not be mentioned in the goal. That's pretty clear. And on top of that, so we're just thinking about adding these objects in the object list of a problem. And beside these two initial conditions, which are quite self-explanatory, there must also be no operator that allows to make some predicate about the object true, with no other predicates to be checked in preconditions. So we don't want something about the one that we have posed in this example in this slide, right? So, which is the traditional case. So generally when you have an operator which is working on an object, you put in there some preconditions about the object that you want to manipulate for checking, I don't know, the characteristic of the object, the positions of the object, and so on and so forth. Then we have another class which is considering domain models where you want to modify, which are inapplicable dummy operators. So we want to add, or we're thinking about adding operators to the model that can never be applied. So you are sure that they will not appear in solutions because they can't be applied at any point in time. And an example is to drop an object that you are carrying. The object has to be already dropped. Of course, it sounds quite stupid in this text, but then if you look at the actual code, it might become pretty hard to spot that this operator is inapplicable, beside the name that we gave it. And another kind of operators are dead-end operators. So these are basically operators which are leading the search to a dead end, so can't reach the goal at any point. So again, you are sure they are not appearing in the solution plan, but you're expecting these to be much more disruptive than inapplicable operators because they can drive a search and then lead to a dead-end state, and so forcing the planner to do some backtracking. And an example here is when you drop an object that you are carrying, the object disappears. Again, in text that's pretty easy. When you look at the code, it is a bit harder to spot this sort of issue and mistake. And this is exactly what we meant by attacks or accidental complexities, which are very hard to spot if you are not going line by line and completely understanding what is written in the model. And now that we have defined these three classes of attacks, or three different classes of accidental complexity issues, we have to run some experiments. So we consider 5 planning engines, 5 domain models, which have been used in the international planning competition. So we believe that they are of good quality, and we are trying to reduce the quality by doing our black magic that we have described before. We randomly generated 20 instances per domain. We used Val to validate the generated solutions against the original models, just to have another layer of security that our changing and our manipulations are not affecting the validity of the plans. And okay, we run that on a machine with 5 minutes CPU time cutoff. And okay, increasing objects. Now, this is the most stupid type of attack, and in fact, it's not particularly effective against planners. But nevertheless, in most of the domains, there are planners which are being affected by just increasing the number of objects, even though objects cannot be used. So if you look at here, you can see that in most of the domains, facts which are instantiated are increased by some size, and that generally there is a small impact also in terms of the runtime for finding solutions. Notable issue is in BFWS, which is the only planner that when you add objects, it reduces the runtime. I don't know why, but that's another thing which is quite interesting. So that can be a way for reformulating the models. Inapplicable dummy operators, most of the benchmark, the engines did not really have any issue with that. So they are very robust with regards to this sort of attack, but in Chrpa, where you can see that in terms of runtime, in terms of coverage, and in terms of grounded actions, there is quite a strong impact. And the last class are about dead ends, and these dead ends can affect very negatively the performance of planners. And we can see here we just reported 2 examples, one in which the impact has been very mild, floor tile, and one where the impact has been quite strong, which is Chrpa. Again, results are reported in terms of time, coverage, and increase in the number of grounded actions. All the results, of course, are present in the paper, so I'm not staying here too much about that. So for concluding, the fact that planning is being more and more used in application means that it must become more and more robust, also with regards to malicious attack that can arise from cyber attacks. So in this paper, we raised awareness about the weaknesses of the planning framework, and we formally defined 3 classes of attacks. We, let's say, formally defined also what does it mean to be hard to spot and fix, and we demonstrate the impact in terms of experimental results that these sort of issues can have on planning engines. What we believe that now is important and pivotal is to investigate techniques and approaches that can improve the robustness of planners. And these techniques can be related to knowledge engineering tools and can also be related to the way in which planners are pre-processing before starting to actually doing some search. And that's it from myself. Thank you very much. And please right now do not start hacking planning system now that you know how to do that.